All right, welcome back to Bill Westlake Programming, and this is the compiler design course. Where we left off, we got a very simple lexer working. If we go into, excuse me, click in here. If we go into our source directory under build and go main, we start the lexer. We can type in some numbers. And hit enter, and it lexes all of those numbers. The lexical analyzer reads them and determines that they are in fact an integer or a floating point number and displays them accordingly. So that's where we're at the moment, and that's done here in this lexer file. The lexer is just using some very simple regular expressions to come up with these numbers. What we're going to do now is we're going to take these and make tokens out of them for the parser. But then we've also got to wire up the parser so it's running as well. So we're going to do that right now. There's just a couple of things we need to do over in the parser file to make that happen. So one of the things that we need to do is we need to have well, we've got we've got a token called float. I needed to put that in. We're going to make another token here called int, and I'll explain what these do in just a second. This is our parser file. Let me expand the text on this. Editor font, zoom in. Make this a little bit bigger so it's a little bit easier to see there. That should be good. This is a kind of language that's referred to as BNF. It stands for Backus-Naur form. I think I'm pronouncing that right. These two guys came up with this way of describing languages, and not just computer languages. They were working with languages in general. The computer science world adopted their format to create these files. This the syntax here is really very simple. In fact, you pretty much, except for some keywords like token and a few others, you supply these words. These are not keywords of the language or anything. This can be anything you want, these names of things. And the format of this is telling you what the language grammar looks like, and that's what we'll go through step by step. But for now, we're going to just kind of put it together. It's a float or it's an int, and those are our two tokens. Okay, so we have names for these things, though. We made up all of these words except for the keywords that are in here, and I'm saying that a program is a line, or this vertical bar means or. It's a program followed by a line. So this creates what's called recursion. This program is the same as this program, and we'll talk about how it reduces and all that as we move through. But basically, this is a format that says this is how a program is formed. It's a line followed by or it's a program followed by a line. So it's recursive. It's as many lines as you want. It's line is a program, followed by another line is still yet a program. And that's what it reduces to as a program. So this defines down here what a line is. And in our case, a line is just a float or an int. That's all we have to work with at the moment, is a float or an int that we're going to parse. Over here in the lexer file, we do need to include something. Hold on one second. Let me take a look at my notes. So over here in the lexer file, we need to include another one, and this is going to be parser.hpp. Parser.hpp is a generated file, and it should be here in the, if we've got a build, yes, this is the build source, parser.cpp, and oh, it's just parser.h. Okay, I think I changed the name in my notes. So it's parser.h. Parser.h is a generated file. It's generated by Bison from this parser.y, and it contains our definitions of floats and ints and other kinds of tokens we will create. And we're also going to create how you can move the data across. So we have that, and what we're going to want to do is, instead of printing this stuff out over here, in fact, I'm going to just get rid of all of this like this. What we're going to want to do is parse these numbers and return a value. And we're going to be returning, in the case of a floating point number, we're going to return that float keyword, and here we're going to return int. And oh, actually we need identifier as well, so we're going to return ident here, and we'll put that over here in our parser.y file. We'll also create a token ident, although we're not going to use this right away, but just so that we're complete and it's there, token ident. Okay, all right. So but before we can return this, we got to have a way to assign the actual number, figure out what that number is, parse it, and put it into the system. So oh, that's right. Okay, so we can just we can do that right here in our code section up here. So oh, and I believe, let me close this. That's a generated file. All right. So there's some things we need to fill in here, and we'll do it a piece at a time. Right now, what we need to do is parse these numbers. And in C++, we can do that very simply. I'm just going to create a very simple function here. And if you're not familiar with things like templates, that's okay. I can explain this. These are simple template functions. We want to include. We've got IO stream pound. We want to include S stream as well. And we're going to do oh, forgot the function. We'll call this parse number. And that's our number string. And we're just going to create this string stream. And then we're going to go SS from string. That just puts it into it. We're going to create a result value and just set it to 0. And then we're going to go SS to result. And then we're going to return the result. And I'll explain this, how this goes. So this template function takes in a type, and it really can only be a float or an int right now anyway. And what it does is it pumps it into this string stream, and then it brings it out of the string stream into a result, which automatically will parse it into the appropriate type based on what this result type is, and send it back to us. So what we can do now is go like this and go parse number, and it's going to be a float, and the value is in YY text. This is a value used by the Lexer to store the actual text that it grabbed based on that pattern. So we have this pattern here of 0 to 9.0 to 9. When it sees that pattern, it puts the text, the string of that, in YY text right here. So we're just going to pass YY text into this string. The fact that this takes a string will take this regular kind of character pointer and put it into a string, and we'll be able to use that string down here. So we can do the same thing with but we need to assign it to something, and that's where we need to get over here to parser.y. 1 second. And over here in parser.y, typically I want to do this up here. Yeah. What we're going to do is create a special kind of union. And this union, it'll get turned into a kind of union, a regular C++ union. But we use this this token here because it's the parser's actually got to interpret this and use it correctly, because this is our way of transferring the actual data types across. So we're going to create two data types in here. We're going to call it int, and we're going to call it int value, and we're going to create another one, float, and we'll call it float value, or we'll just shorten that to val, float val, int val and float val. And so working with this kind of stuff, there's kind of a back and forth. The parser and the lexical analyzer have to communicate with each other, so it's a little bit difficult to explain one side without explaining the other at the same time. So what we can do over here then is make an assignment like this. This structure that we're working with is called YYLVal, and it's dot float val equals that parsed value, and then we'll return a float token. And like I said, I'll kind of, as we put this together, we'll go like this: YYLVal dot int val equals parse number int YY text, and then we'll return an int. So the return value of int, which is the token, tells the parser I got an integer, and the parser knows to find that in the int val point of the structure, and we're also going to tell it that, and I'll show you how. So what we're going to do is go here, and we're going to set up some types now for these tokens. Actually, so I used token here, but actually I'm going to give these types, and I'm going to do it like this, and I'm going to say this is a float val, and I'm going to give this a type called int val, and we'll get into some other things later. This is actually going to be a string. We won't set that up right now. We've just got the float and the int. Okay. There is one other thing that we do need here. We've got, let's see, we need a couple of functions, and these functions need to be, so we need to up here create a function. We probably need to include some things in here too, but we need to do this again, just like we did over there, so we can write some code in here. And we need a function called int, and it's going to be called YY error, and it's going to take a constant char pointer, we'll just call it P, and we'll do something with it like we need to do some includes up here. We need to include IO stream at the very least. Then we can do standard error from P from endl, standard endl. And I suppose I can do this. I can come up here and go using namespace name space standard. And then I can get rid of these, simplify the typing a little bit for our purposes. I don't mind in this case if all that gets imported. We're not going to step on any namespaces anyway. Now we got one more thing to do to tie in the actual compiler, and that is to go into our main function, and we need to call the parse function. So where's our main.cpp? So here we're saying while yylex. We don't need to do that anymore. We're bringing in, so extern yylex, we need extern int yyparse, and now we just need to call yyparse, and we should, I think, be compilable. Let me move up here one, and let's do a build and see if I made any mistakes. I got an error. str was not declared in this scope. Interesting. Okay. That's in lexer.l 1311. So lexer.l, oh, I'm already using namespace standard. Is that the problem? Oh, string was not declared in this scope. Lexer.l. What am I looking at here? Not seeing. Oh, it's numstring. Okay. Try it again. Okay. I didn't do a very good job of that. Let's try that. So undefined reference to yyparse. Why are we not getting this in function yylex? Is it yy? What I do wrong? So part of the problem is I'm looking at notes that are written a little bit differently than this. Is it yyparse with an underscore? No. Hold on. I'm going to simplify this. I'm not going to use this main function. Let's go into here. No, not that. See, make list.text. That's the cache. I don't want that. Where am I? Here it is. CMake list.text. I'm going to take out main.cpp. And in main, I'm going to copy this main. Go to parser.y. Go down here. And put it in here. That should give it access to everything without the difficulties of using a separate file. Oh, what doesn't it like now? Undefined reference to yyl-val. Oh, duh. It's yy_l-val. No, it's not yyl-val. All right, let me pause the video and look into this. See, in my example that I wrote a while back, I defined a different prefix. So it's some of the names are changed, and I do that so that I have a different naming scope for things, and that makes it look a little different than what I'm expecting here. So let me see, what do we got down here? It's just... Okay, we're back. Yeah, I forgot to include this extern int yylex and yyparse up here at the top, and I had one other problem with it was over here in yylex. No, that was mainly it. Yeah, So we have to declare these two externs here. Oh, yeah. One other problem was I had this Bison main parser outputs here commented out. So it wasn't linking the parser in with the main, and then it was seeing an error over in the parser side because things weren't linking up. So yeah, make sure if you commented that out, or if you're following along, uncomment that line and add these externs in so that it has access to it, and then the main function will work down here. So we can build it now. I'll build it. Make clean. We'll do a make. It builds. If we type in .slant source slant main, it's starting lecture. Well, we got to take that out. So 1, 2, 3, 4, 5, 6. But now it's not going to do anything because we haven't told it to do anything. But it didn't put out an error, which means that it recognized that just fine. So let's now have it put something out in here, just like we did before. So what the way I'm gonna do that is here when we get whenever we get a line, actually, which will be a number. Let's just do this: cout from line. No, actually, let's not do it here. I'm sorry. Just like we did in the lecture, whenever we get a float, let's say something. So here in these braces is code that'll run when the parser matches up a float. When it sees a float token, it'll run what's in here. So let's output it. Let's go cout from float, and now the value, this is a little bit weird, but we're going to put in here $0, okay, and then endo. All right, so let me explain that. So inside the parser generator, there's these special symbols beginning with a $, and there's they are $, which represents the whole, this whole thing combined. If there's multiple things in here, the first it represents the result of this, what's called a production. $0 is the first item in it. You can have multiple items, like up here we have program and line. So program in this sense is $0, and line is $1. They're like placers, they're like placeholders, but they contain actual values. And what values do they contain? They contain these values that came back from the lexical analyzer, and they contain the correct one because we've told it what that token is here, so it knows what the type of this is. So for a float, it knows that $0, which is that float token, which is a terminal, and is here, it's a float value. It knows that it's this float value right here. So we'll do the same thing here for int. We'll just copy this and paste it here, and we'll make this say int, and again $0, because that's the $0 position. I don't know why it did that. Okay, so let's see if we can build that. And this at this stage is just kind of what doesn't it like? That's a lot of errors. No, it's actually mostly just warnings of some kind. Let me, you know what I said before, I'm going to use this one because it's bigger text that you can see. So we've got an error right here. No type name type instruct enable if false basics. So that's something deep inside the system. Let's scroll back to the top. There's got to be an error up here. Error, no type name type instruct. Huh? that doesn't make a whole lot of sense, really. Looks like we ran out of scroll back in that one. All right, let's try to see what's going on here. See out from int from that doesn't make any sense. Well, so I'll put this in. I think this is what it's complaining about. Maybe. And I'll explain this. This is just moving the value of the float into this overall position. It's saying that, or actually it's the result of this, which becomes the result of this, which becomes this value up here, assigning it to $$. That might be what's causing the issue. And once again, I said I would use the other terminal, but maybe this one's got a bigger scroll back buffer for all these errors. Here's the top level error. Operand types, basic extreme, YY parse, S type. Doesn't like that. Why does it not like that? Oh, I'm sorry. It's not $0, it's $1. Yeah, that's what it was. Little Oh, that's because I don't have line as a type. So we have to go percent type int val line it worked. It compiled. So I'm telling you, so I might not be explaining things too much right now because I'm trying to kind of do an overview of what the thing's like. And so it can be tricky. A little typo can be hard to track down. So you got to be real careful and you got to remember important things. What I had to do here was I had to define the type of line because I'm assigning it here. So it's got to know $$ is what line is, and $1 is this int and this float. I turned it into an int val, and I can't really do that, but it did compile. It's going to truncate. Line would ultimately truncate it, but we're printing it here, so it's okay. It would cast that float into an int, and it would lose some data. We've got to change this. So that an int and a float can be something like an expression and have an appropriate type. So let's do we did the make, it worked. Okay, so let's run it. ./source main, and let's type in some numbers: 1 2 3 4 5 6 7 8 9 and 1.2, and now we're parsing it, and these are actual numbers in this case instead of just strings. The parser's putting this out, not the lexer. When it found the int and it found ints and it found a float at the bottom here, but we can't do this. What we really need to be doing is putting them into a different kind of type, a class of some kind, so that we can have a higher level thing called a number that can store, it can either be an int or a float. And we'll talk about that when we talk about abstract syntax trees. But for now, what we can do is we can start building up this idea of expressions that do multiplication and division and so forth. And we can turn those into something that's that's useful. In fact, that it can be an expression. So let me check the time here. We spent a little bit of time troubleshooting there. Now we're at 33 minutes in this video, so I think that's going to be it for this video. Let me quickly overview what we've done. So we've created a number parser here, and that number parser is used to translate the text, the string that you typed in, into an actual floating point or integer value, and it can convert both, as you can see. It's a template type, and I'll explain more about template types as we go along. And basically, this just says the compiler is going to generate two different functions is what it's going to do. We're using it for ints and floats. The compiler is going to take this little template function and it's going to create two functions, one that takes a string and returns an int, and one that takes a string and returns a float, and that's really what templates do. Templates get very complex. You can do some amazing things with templates, but in their simplest form, that's the easiest way to look at it. It's just going to generate different functions for us, so we don't have to write a function for floats and a function for ints and a function for doubles and booleans and whatever. We can translate anything with this that is translatable in this way. So the lexer pattern matches individual characters to come up with groups of characters that form a token, and the token, along with any associated data, is returned to the parser. The parser uses pattern matching of tokens to find a pattern that matches the grammar, and it runs an appropriate executable section of code whenever it finds that. And we can see that here. We're still running. You know what? Let me kill this and go over here so it's bigger so you can see it. And we'll go dot source main. So here it's running. We can go 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2.2, 42.7. And it finds all those. We can do it again. 1, 2, 3, 4, 5, 6, 7, 8, 9. And it finds them. Whatever we typed in, it's just parsing them and outputting what it says to do for that, what we call a production. And that's what's happening in here. It's finding this pattern. It's saying, I got a float token. What do? I run this code. And so forth. So this is just our main function. I was just having trouble with linking. We can actually probably move it back to the main. I like to keep it separate. Some people like to put the main right in here. The main function for a real parser can get a little bit complex, and I like to have it in a separate file because I like to be able to create additional functions to handle certain things. When we start actually working with files, we'll want to open files in here and so forth and attach it, and I'll show you how we attach to the parser. This part, the initial videos in this video are just kind of an overview of what it looks like to do a lexer file and to do a parser file in Flex and Bison. I think in the next video, we're just going to take a quick look at expressions, and I'm going to explain what an expression is and how we parse it and what it looks like, and then how we would set that expression up in here so it can actually evaluate things like addition, multiplication, and subtraction, division, and so forth. So that's it for this video. Thanks for watching. I hope you enjoyed it, and I look forward to seeing you in the next video. Thanks. I hope you enjoyed the video. If you liked it, hit that like button. If you really liked it, hit that subscribe button. And I hope to see you in the next video. Thanks for watching.